All right, everybody, thank you for having us. So I'm Srinath Vadlamani from ARM. Unfortunately, Darren Seppanopoulos wasn't able to come to this meeting. He had to go to UK to talk about the catalyst that we heard earlier today, that catalyst announcement. So I'll go over what ARM's bringing to the HPC community in terms of a new solution. The title, Transforming HPC, I don't know about that. Through all the conversations I've had over the past day and a half, has HPC really transformed over the past 20 years? No. Okay. So, what ARM is bringing to the table? We are in the mission of actually getting an ARM supercomputer on the planet, if not many of them. And we're doing this primarily through three strategies. So we have this enablement concept, a co-design concept, and a partnership. Enablement, that is where I get to play. It's a lot of talking to customers, understanding what their concerns are, what their desires are, and offering up both tools and opportunities for our field engineers to go in and help them accelerate and optimize their codes on their HPC platforms, use that information, bring it back to ARM so that we can talk to our vendors to actually enhance hardware down the road. Similarly, there's efforts going on to actually co-design the actual architecture itself, or the microarchitecture itself. So again, I should ask the question, who here owns an ARM chip? You actually own a chip that ARM makes? Do you? No, you don't. So we actually create IP. We create an architecture of which vendors either lease or buy from us and create actually silicon chips. So we created the recipe book and we give it to the cooks and they make their meals, right? If you can think of that concept. And we, by having them lease the IP, they adhere to a contract so that there is some level of mutual communication among other platforms that are also ARM Arch compliant. If they buy the actual architecture, they can do whatever they want with it, right? And there are people in the world that have done that. They've spent multi-millions of dollars for that. When it goes to the leasing scenario, they lease it, they manufacture silicon, and then they pay us royalties when they actually sell it. So we don't actually make the silicon. So as the conversations go forward, remember that. We don't actually make the silicon, but we sure as heck want silicon, our vendors, to be successful in selling it and making everybody's jobs a lot easier when it comes to scientific computing, machine learning, and we're also doing really well with everybody's phones working better, right? So you are people that were suspecting that phones are ARM chips. They are ARM-enabled chips. They run the ARM instruction set on them, okay? I don't mean to be crass. Sorry, I didn't mean to do that. Okay, so we have these institutions that we are working with regards to microarchitecture, or architectural designs and microarchitectural designs. Yes, we do at ARM design microarchitectures that people can actually lease. And that's your similar, like your Cortex line of chips, the A47s, the A72s that we hear people talking about. Those are our microarchitectures. We don't fab them. Someone else has actually got a factory that fabs them and sells them out. Now, in that code design, we offer solutions, offer ideas that we're getting from our customers, customers being labs, being people that are actually wanting to use these chips, feed it to the vendors. They're able to adjust their designs, give us quick returns to new designs, and offer them up for people to use. And I'll show you an example of timeline with regards to the ThunderX line coming from Cavio. So then we also have this third tier, or this third component called partnership. So again, we are working with the partners to go through architectural designs. We also are looking at independent software vendors with regards to their software stack and understanding how to enable them on ARM and enhance their performance on ARM-enabled chips. So what we're bringing, you have a 64-bit architecture that is made for modern workloads. Modern workloads are compute-intensive workloads and memory-intensive workloads. These are the classic HPC problems, our scientific codes. So the integration of the SoCs, we're really paying attention to how the memory hierarchy is working on these SoCs, offering up suggestions to the vendors on how to stack their memory, how to play out the memory, how to put a lot more channels, why you would want a lot more channels to the memory type of thing, right? There's a statement here about a cloud solution. Hopefully people are understanding that there is a crossover in terms of high performance computing needs and server needs. There is a crossover, and hopefully people realize that's our memory bound scenario, right? It's a game about getting memory to work well for you. So both communities can learn from each other, and we're definitely having that cross dissemination within our internal groups at ARM. Commercial and open source software for HPC. So we are selling compilers, we're selling tools for the HPC community, and we're also offering up our solutions to the open source community. Everything we put into our compilers eventually gets pushed back to the open source community through the GNU project, okay? You can think of it as having maybe 6 to 8 months lag before they accept it and put it into their release. So we have partnerships all over the place. And then we have the nice fun statements that we like to say about ARM. You know, we do really well. We have 125 billion ARM core chips shipped over the last 25 years. Yeah, everybody's phone's got an ARM. So mobile, embedded, hopefully people understand the auto functionalities. There's ARM chips in all your cars, infrastructure, monitoring of power grids and so forth, and the IoT is a big space for us. So to go over some of the HPC deployments that we're looking at, and in reference to the ThunderX chips. So we have, Cavium is committed to putting out the HPC class server chip called ThunderX, and the ThunderX 2, well, we're talking 3 years into actual development and coming off a fab floor, has shown a 3x speed up on many metrics, be it flops, be it memory. Pretty good in my book. We have partnerships that are in the bottom left-hand side of that triangle that exists today, and then we have deployments with companies that are happening right now and in the future. I'd like to highlight HPE, Cray, and the institutions that they're at. So we have Oak Ridge as being a partner that's actually working with deployed systems. GW4, we hear it mentioned before, the Isambard project that's going to GW4. They're doing great work in evaluating the efficacy of ARM chips. Bull Technology is working heavily with ThunderX2 enabled racks. And Penguin Computing is actually putting out ThunderX2 racks, which is news to me. I didn't realize that. So here is a listing of a number of off-the-shelves items that you can actually go out and purchase. We've mentioned HPE. We have Penguin, Atos, which is the Bull Sequena, Cray, XC50 supercomputer. That's what Isambard is demonstrating, and Foxconn and Inventka. I haven't played on all of these, and I don't think anybody has played on all of them, but they're out there to start working with. HPE has worked heavily to get an ARM-enabled chip out into the HPC community. And so I want to highlight the Apollo system. That's what's actually being deployed as the production system. The Cavium ThunderX2, okay, it's 32 cores, 64-bit, and right now it's ARM v8.1 compliant. It's actually going to be A2 compliant also. And does that mean it actually issues instructions for every one of the instructions that are in the actual ISA? Maybe not, but it will have something that will mask the functionality. So here's some numbers. I think the slides are going to be distributed, right, as part of this forum, so we'll just move on. So This slide hopefully convinces you that we're serious. We got an interconnect solution, that we're working directly with Mellanox to work on a proper solution for these systems. You may say, hey, they've already come up with interconnects. Why do you even have to do anything new? Well, you're talking about a RISC programming model, out of order memory, weak ordered memory model that needs to talk to a NIC, that needs to push to another node. We know that IBM with the power systems have had some experience with this, but this is a whole different, well, there's a lot of differences that go along with our RISC chips. So drivers have to be rewritten, and they have to be tested and pushed across fabric. So, and we're doing that right now. So hopefully, as HPC community, when you see an interconnect slide go up, you know that people are serious, because that's part of the scaling game. Want to highlight the Craze endeavor and also enabling or getting the ARM-enabled chips out there, particularly the ThunderX2. And Eisenbard, here are some results that I didn't see the earlier talk present. And this hopefully convinces some people that there's some efficacy in looking at a ThunderX2. Got some memory, good benchmarks that are up there. Who here is not familiar with these kernels that are at the bottom when it comes to HPC benchmarking? Okay, everybody is. Hopefully everybody picks up on a x-axis going from left to right with regards to a computational intensity metric, right? So a memory solution, definitely been demonstrated here. We've got some work to do here. But hey, ThunderX2's VPUs are half the size of Skylakes. So we're not doing that bad, all right? Crank through the numbers, start matching them up, and you start to see where we actually lay when you try to do apples to apples comparisons. More comparisons, these are actually more of a physics model type of benchmarks. And again, we're seeing a lot of efficacy. And this is a full-blown comparison against Skylake. So you'll have these in your slide deck when you actually check this out. Here's the Catalyst project that was announced yesterday. And we have commitment for the Post-K computer to be an ARM-enabled system built by Fujitsu, making the cores. Now, we also offer up in our solution stack actual software. So we're presenting the world compilers, performance libraries. ARM Forge, Alinea was recently purchased by ARM, so the DDT and the map, the DDT debugger and map profiler are now part of ARM. And then, of course, performance reports is part of the original Alinea software stack. So here is a quick review of what the debugger is. You're going to have this in your slide deck, so you can revisit it. And then you have a profiler. Hopefully everybody here in HPC knows how to use a profiler to understand where their hotspots are on their codes. And hopefully everybody here has tried that at 100,000 cores and have pulled, sorry, I wouldn't say pull your hair out. That's not fair. Then you have performance reports, which is a really quick way of getting an idea as to where your hotspots are in your code themselves. Lastly, I'll leave you, well, actually, I'll go through what our group does, which is offer up actual services to enable partners and customers and future customers to use ARM as an HPC platform. I go to labs, I sit next to computational scientists and roll up my sleeves, and we work on code and we make it work better. Not only on ARM, on x86, on all platforms. So we complement the whole community by raising up all standards with the efforts we do. So here's some useful links. I'll leave this up. This is the last thing I'll show. Useful links to a community forum that actually discusses ARM, where you can get the software, and also recipes on how to port to ARCH64, and where to make all your complaints. All right, leave it at that. Thank you, everybody.